let's keep fingers and everything else crossed that you then can see the screen without it freezing. The recording is coming up. Good. And I need to share the screen. And let's hope that you can see the screen. Can you see it? I think there's a little bit of a lag again, which does not bode very well, but let's keep everything crossable crossed. And let's not do any funny things today. Good, brilliant. Thank you for the feedback that you can see everything. Right, and we'll give people a little bit more time. By the way, you got my email yesterday about the link with the links in it, didn't you? Yeah. Okay, good. And I suppose next week I will say a little bit more about this assessment, but you know, don't stress too much. If you get less than 100% in this assessment, then there's something not quite right. Yeah, the chat is lagging. Yeah, I can see that. It's really strange. It's almost like, you know, since Kent is now in tier 3, or is going into tier 3, Teams is switching off. Oh, that's the assessment, what is labeled as ICT in week 12 on your timetable for BI 308 for the Skills for Bioscientists module. That's this assessment in week 12. We are still quite a bit away. Yes, I haven't decided exactly how much time I give you, but it's not an assessment that is trying to put you under pressure. Yeah, no worries. No worries, Var. And it is recorded anyway, so don't worry about that. And please keep yourself muted. How many more sessions on buffers do we have left? Well, I hate to tell you that, but I think my plan is to finish it today. Because I want to move on next week and do something new. So let's get started, hey? Because what I want to do with you today, I want to really give you a little bit of an application of this Henderson Hasselbalch equation. Because I think this is really interesting. And what I want is to do is also turn things a little bit on its head and actually make a link to the BI 300 module, where we looked at proteins and amino acids and things like that. But fear not, if you haven't done this module, it's not essential that you really have done or all of that stuff. I hope everything will be clear anyway. So for the last couple of sessions, we were discussing buffers, and I told you that buffers are absolutely essential things because they excuse me, I've got a frog. They allow a system to maintain a relatively stable pH. And I told you also that, for example, in the blood, we need to maintain a very, very tightly controlled pH. So in the blood, the pH, pH is between 7.35 and 7.45, and anything outside that would be actually fatal. It would be lethal. So if your pH drops to 7.2 or something like that, there's a good chance that you will not see Christmas, or actually the end of this lecture. So we need to maintain a really, really tightly controlled pH in the blood. Oops, what was that? Cancel. This is weird. This is really weird. Okay, good. Now you know my passcode and I have to reset it. Don't you worry, I'll do that. But we can look at it also from a slightly different point of view. And we can say, for example, okay, let's have an acid. Yeah, right. We have an acid, and this acid dissociates into H plus plus A minus. So here, this acid, obviously this is the acid, and that is the conjugate base. Let's put it this way. And this acid dissociates, and we can define this pKa, this dissociation constant, for this kind of acid. And we also see something interesting if we look at these two things, because the acid, what is the charge of the acid? What's the charge of the acid? Yeah, absolutely. It's neutral. And what is the charge of the base? What's the charge of the base? That's -1. Absolutely. And we need to work with that later on, so bear that in mind. Now, we can formulate the Henderson Hasselbalch equation. So pH equals pKa minus log of the acid concentration divided by the base concentration. I put a bracket around so that we get this, we know how we can deal with it. And I showed you how we can very easily rearrange this equation. And we get the acid over base ratio. And I'm just too lazy to put the brackets around that. Acid over base equals 10 to the power of pKa minus pH. So far, so good. That's what we have done yesterday. So, what are the implications of that? Well, if you think about it, if the pH is smaller than the pKa, what do we get then? So acid over base equals 10 to the power of, again, pKa minus pH. And if pH is smaller than pKa, is this bit here larger or smaller than 0? Is it positive or negative? If the pH is smaller than the pKa, yep, it's positive. Absolutely right, it's positive. That means we would have, if we just look at it like that, we would have more acid than base. And I think that is something that we looked at it yesterday. If the pH is smaller than pKa, then we have more acid than base. Okay? Does that make sense, John? What happens if the pH is smaller than pKa? Larger than pKa, I beg your pardon. Acid over base equals 10 to the pKa minus pH. What would that be? Is this pKa minus pH, is this positive or negative? So it would be more base. More base than acid. And we can even be more specific. We can say, for example, if the pH is 1 unit smaller than the pKa, what is our acid to base ratio? What would that be? More acid, yes, but we have a pH that is 1 unit smaller. So let's say 10 to the power of, let's say pKa is 5, pH is 4. 10 to the power of 5 minus 4, that gives us 10 to the power of 1. So in this case, we would have 10 times more acid than base. Okay, does that make sense? So we would have acid equals 10 times base, or 10 times more acid than the base. Okay, what about pH is 1 unit larger than pKa? What happens then? pH is 1 unit larger than pKa. What do we get? How much more base? You're absolutely right, Reynolds. How much more base? So let's say we have 5, we've got 6. So acid over base equals 10 to the power of 5 minus 6. So that gives us -1. So we've got 10 to the power of -1, which is the same as 1 over 10. So in this case, we would have 10 times more base. Yeah, does it make sense? 10 times more, absolutely right. What about the pH is 2 units smaller than the pKa? What can we say about acid and base? Let's just try that out. Let's say we have pKa of 4 and the pH is 2 units smaller, so pH is 2. So if we've got acid over base equals 10 to the power of 4 minus 2, that gives us 10 to the 2. So that gives us 100. So we would have 100 times more acid than base. It's not 20, be careful. It's logarithmic. It goes with the power of to the power of 10. So it's 100 times. Oh, I just made that up before as an example. So when I said pH is 2 units smaller than pKa, I just picked 4 and 2. I just as well could use 8.7 and 6.7. It's the same thing. It's just a difference of 2. Yeah. So we can, if we know a pH and the pKa, we can figure out what the ratio of acid to base is. Which one is predominant? Acid to base. That is what we can very easily determine, right? And of course, that can have massive implications. Because if we have, for example, if we have an acid like HA and A minus, this one is uncharged, whereas this one is charged, right? Okay, so far you're with me, you get it? So if we have a pH and we know the pKa, then we can very easily figure out how much of something, of a compound, is charged in the charged state and in the uncharged state. Okay, so now I've got a little brain teaser for you. If we have more base, and I write it like that, then we would have 10 to the power of something negative. Absolutely right. Now here is a little brain teaser for you. I have a compound, right? And I draw this compound, and you tell me what compound this is. Daria, yes, it is an amino acid. Absolutely right. Very good. Amino acid. Which one? Ah, yeah, good, James. Excellent. It's alanine. And you know that it's alanine because it has a CH3 group here. If it was glycine, it would just have a proton here in this position. So it's an amino acid, and it's the amino acid alanine. Okay? Now, tell me, how is alanine, the amino acid alanine, what is the charge of this amino acid? Yes, you are supposed to recognize all the amino acids. It's a Zwitter ion. So what is the charge? It's neutral. Reynolds said it's neutral. So the charge is neutral. So the overall charge is 0. Okay? This is what Reynolds says, and Daria confirmed that. Are you happy with neutral? Charge is 0. Do you agree? I'm just interested in the overall charge. Are you happy with that? That it's neutral? Yes, but probably not. Mokam knows me quite well, actually. Actually, your answer is good. Your answer is good. And of course it is a trick, but it's not correct. So the charge is 0 might not be correct. Give me another answer. What is the charge of the amino acid alanine? It's neutral under physiological conditions. Ah, that's an interesting one. Thank you, Bernardo. Yes. Under physiological conditions. Schimmick made a really, really good point here. Let me put it this way. What would happen if I took this amino acid, our little alanine, and I put it into an electric field? So I've got the negative side, which is the cathode. And I've got the positive side, which is the anode. And which direction is it going? Is it going this way, or is it going this way? Or is it staying put? Ah, does it depend on the pH? Does it depend on the pH of the solution? You are onto something here. Now let's have a look at this thing. HN CH CH3 COH. It does depend on the pH, but how? How does that work? Well, we have got two groups here. We've got this one here, and we've got this one here. And both groups have certain properties. So, for example, what would happen if we had a very, very low pH? If we had a very low pH, we would have the following situation. We would have H2N, and I'm too lazy to draw the rest of the thing. I just indicate that with this line, plus H plus gives us, no, I'll write it the other way around, H3N, it's positive, and I can also write it the other way around. I can write it as H3N plus gives us, oh, I need to work on my handwriting, gives us H2N plus H. Yeah, we can write it like that. And likewise, we can write for our acid side, COOH, gives us COO minus plus H plus. So if we have lots and lots of protons around, we would have the left-hand side as H3N CH3 COO minus, COOH. We have lots of protons around, low pH. Okay? At low pH, very low pH, the amino terminus is loaded with the protons, and therefore, at low pH, we have a positive charge sitting here. So at low pH, it is positively charged. It's the other way around. At very high pH, this line here, do you mean this one is, I'm just too lazy to draw the rest of the molecule. That's this thicker line here. It acts as a buffer, but it also, if you like, yes, it acts as a buffer. It can act as a buffer, but also the pH of the solution determines whether the amino acid is charged or not, and how it is charged. On the other hand, if we have very high pH, at a high pH, what happens at a high pH? Well, at a high pH, it would take away one of the protons from this side here. So we would have an H2N, and it would take away the proton from the CO minus, from the COH, from the acid here. So at low pH, we have NH3 plus. Yeah, no, that's not good. Let's write it like that. H3N plus and COOH. That's at low pH. And that gives us one positive charge. At high pH, we have one negative charge. And somewhere in between, so between low and high, well, we would have a positive and a negative charge. And in between, these two charges would cancel each other out. We would have a charge of 0. So under physiological conditions, the overall charge would be 0, and our alanine molecule would stay put. Under low pH, this thing would be positively charged and would walk to the cathode, so low pH. Under high pH, it would be negatively charged and would go to the positive pole. And under pH 7, this would be probably neutral. It would carry a positive charge on the amino terminus and a negative charge on the carboxy terminus. But we can actually go a little bit further, and we can actually define this point. This region where something does not have a charge, no charge, this is actually called the isoelectric point of the substance. Isoelectric point. It means it is neither positive nor positive or negative overall. The charges cancel each other out. That is what isoelectric point actually means. And very often it is abbreviated as IP, isoelectric point. How do we calculate this isoelectric point? Well, in the case of the amino acid alanine, it's pretty simple, pretty straightforward. What we can do is we can say, right, let's draw the structure again. CH3, COOH. And I've drawn it in the total acidic form. So this is an acid because it can give off a proton, and this is an acid because it can give off another proton. And one can look up in tables what is the pKa of this acid. The pKa of this acid is 9.69, and the pH of this acid is 2.34. And so we've got two acids here. And for the isoelectric point, Daria already has the right equation. It is pKa1 plus pKa2 divided by 2. So that's the equation for the pKa. That applies to all amino acids. Absolutely right. Although there's a little twist to it. Are you ready for that? There's always a twist. Ah, yes. We can run into some problems. All amino acids have an amino terminus, that's this one here, and have a carboxy terminus. And if you think about it, every protein that we are dealing with has an amino terminus and a carboxy terminus. So we could even apply this isoelectric point, not just to a single amino acid, we could apply it to larger polypeptide chains. And every protein also has an isoelectric point. Now let's explore that a little bit further. Let's draw another amino acid. And obviously you can tell I love my amino acids. And I draw it already in the totally protonated form. Right. What have we got here? What is this? It's an amino acid, I know, but which one? Yep, it is cysteine. You're absolutely right. So cysteine, and you realize that because it has an S in it, and there are only 2 amino acids with an S. Where's an E? That's a C. That's the central carbon. Sorry. Okay, so for cysteine, where are our acids? Well, of course, this one here could be an acid because H3N could give off a proton. We've got here an H and we've got here an H. So we have not just 2 pKa's, we have 3 pKa's. So here, this pKa is for cysteine is 1.71. For the carboxy side, it's 10.78. And this one here is 8.33. So we've got 3 pKa's. Oh, for fuck's sake. Good. So we've got 3 pKa's. How are we going to deal with that? Now, let's see what happens. If we have a pH of, say, pH of 0, so very low pH. No, it's not over 3. And that is where the twist comes in. And I'm glad that you asked that, because that is the obvious thing. Let's look at pH 0. So we are very, very acidic. We know that acid over base equals 10 to the pKa minus pH. That was our starting point. Now what have we got? We have H3N, and here is the thick bar which indicates the rest. Dissociates into H2N plus H plus. That's one. Then we do the other one. SH dissociates into S minus plus H plus, and we've got COOH goes into COO minus. So these are our three acid functions that we potentially have. So this is what we have. Now, at hang on, I just noticed this should be the other way around. My pKa's 10.78 and 1.71. I've noted it wrong, but it doesn't matter. If I want you to do a calculation like that, which is rather unlikely, I will give you pKa's. So don't worry about it. So if we are very, very acidic at pH 0, we have everything in this sort of acid function here, right? So what is the charge at pH 0? It's still here, don't worry. I was just too lazy to write it. What is the charge at pH 0? What do you think? It is, you're absolutely right, Wisdom. It is positive. We have one positive charge because this guy here is in this state. It is positive. Absolutely right. Now, what happens if we go to, say, pH 1.71? What happens? We still have H3N. We still have this guy here. What about our COOH? What happens to this? Well, the whole molecule would be positively charged because the amino group is positively charged. But so if we've got pH of 1.71, we can calculate the acid to base ratio here. 10 to the pKa minus pH. So here we've got 10 to the 1.71 minus pH 1.71. So that would be 0, 10 to the power of 0. And therefore we get the ratio of this would be 1. So we would have the same amount of this acid and this one. The SH would not change. So we would have a mixture of positive and negative. Why is it positive? Well, let's just simply do the ratios. We can do that. Let's say we have H3N over H2N equals 10 to the pKa minus pH. Okay? And we said the pKa for this guy is 10 to 10.78 and the pH is 0. So we have 10 to the power of 10.78. Which one have we got more? Do we have the H3N or the H2N more? Which one is more in this case? If we've got that. We are back at pH 0. So we have loads of the acid. So it's basically all of it is in this H3N plus. Absolutely right. If we did the same thing for the COOH versus COO minus, we have 10 to the pKa of this one was 171 minus 0. That gives us 10 to the power of 171. So we have this guy here still predominantly in the acid. And the last one, SH over S minus equals 10 to the power, what was the pKa for that? 8.33. 0.33 minus 0. That gives us 10 to the power of 8.33. That means, again, we've got everything in the SH. No, don't cry. Don't cry. It's not that bad. Oh, the reason I had to swap it was because I've written it in the wrong way around. The amino group is 10 to the 10.78 and the acid is 1.71. I just wrote it the wrong way down. My apologies for that. Dividing these things, that is from the Henderson Hasselbalch equation, and it tells us what the ratio of the acid to the base is. So at pH 0, that I've used here, pH 0, at pH 0, everything is in the acid form. At pH 0, everything is in the acid form. Shall we have a quick look at what happens at pH 7? H3N, H2N, 10 to the 10.78 minus 7. That gives us 10 to the power of 3.78. So at pH 7, which one is predominant? H3N or H2N? H3N, pH 7, H3N. Absolutely right. Let's look at the COOH versus COO minus. 10 to the power of, what was that? 1.71, I think it was. Yeah. 10 to the power of 1.71 minus 7 equals 10 to the power of negative 5.29. Which one is in the dominant form? COOH or CO minus? Aha! This one is in a dominant form. And what about the SH group? SH over S minus 10 to the power of 8.33 minus 7 equals 10 to the power of 1.33. Which one is in the dominant form at pH 7? Absolutely right. So, what do we have in terms of charges? We have a positive charge here, we have a negative charge here, and we have a neutral charge here from the SH group. Does that make sense? So hopefully what you have seen now is how you can, when you have given a pKa value and a pH value, you can figure out if one group is in the acid or in the base form, whether it is charged or not. And with that knowledge and a video that I will post, you can calculate at which point the protein or the amino acid will no longer move. So in our case here, this guy here won't move at pH 7 because the positive and the negative charge eliminate each other and the charge on the SH group is neutral, so nothing happens. So with this little thing, you can figure out if, for example, at pH 7, the cysteine, this one here, whether it is in the S minus or in the SH phase. You can say, right, if it was, let's say, at pH 9, again, we would find for the NH3, and I know that people are leaving, so don't worry about it. We have 10 to the power of 10.78 minus pH 9, so that's 10 to the 1.78. Which one is in the dominant form? It's this one. We are always working from the acid function. So in the case of the N, it would be the NH3, that would be the acid. The COOH, that is the acid, and the SH is the acid. So we work always from the acid. For the COOH over COO minus equals 10 to the 1.71 minus 9, and that is 10 to the minus 8.29. Which one is the predominant form in this case? COOH or CO minus? It's the CO minus, exactly. Oops, I wanted this one. And if we look at the SH over S minus, 10 to the 8.33 minus 9 equals 10 to the minus 6.7, 0.6.7. 0.67. Which one is in the dominant form? It's the S minus. So we have a positive here, we have a negative here, and we have a negative here. So overall charge of the molecule would be negative. So for each pH, you can figure out which form is in the dominant one and what is charge contribution. I'll post a video that shows you how you can actually calculate the PI of more than one amino acid. But I'm not going to ask you to do that. I just wanted to show you that we can turn the Henderson Hasselbalch equation around and not only use it for buffer calculations, but we can also calculate what species, what is the charge status of a group under different pHs. So for this one, we had the pKa, so SH is S minus plus H plus, and here the pKa was 8.33. And overall, if the charges eliminate each other, plus and the minus here, that would eliminate each other, so it would be neutral. But we've got this negative charge here from this group down here, and therefore the overall charge is negative. So at pH 7, let's go back to pH 7. At pH 7, we have one positive, one negative, and one 0. So the pH, at pH 7, it would be neutral. At pH 0, it would be positive. So we've got positive at pH 0, neutral at pH 7, and negative at pH 9. Does that make sense? So with that, I think you had enough of chemistry. I wish you a good weekend. And next week, we will start a totally new chapter where there will be lots and lots of nice calculations. And I promise you, because we are going to start with the topic of kinetics. Yes. So thank you very much and enjoy your weekend. Well, there is no really a book because I don't use a book, but there are lots of videos. So just to let you know about that. And I'm not going to ask you that in any tests, so don't worry about it.